So a couple of months ago, I took kind of a deep dive into the Q960 and the Q963 combo. At the time, I was trying to drive multiple devices from the Q963 and the output would choke. According to the specs, it's not a full-size gate. Instead of 0 to 5 volts, it's 0.8 volts to 4 volts. I was curious why that was the case and what could be done about it, and so this is what I found out. So the 963 is completely passive. It just has diodes in it. And if you look at this schematic, on the top, we are getting gate 1 of the 8 gates. Goes into a switch, and the switch decides whether it goes into the diode on the left or the diode on the right. That pulse is 0 to 5 volts and 100% duty cycle. And so that's part of the problem. If you have multiple gates side by side that are all 100%, then you basically end up with one long gate. And they needed to have a break in between each step. So it turns out they have a clock in the 960 that's a 90% duty cycle. So if they brought that over and kind of superimposed it over those gates, they could reduce the duty cycle to 90%. They did it through a diode matrix, which is fine, and they had to use some resistors and so forth for isolation. But what ends up happening there is they lost the size of the gate. So if you're just running it into a regular envelope generator or a couple of them, it's not a problem. But there are some other modules that you might want to use that gate for, and maybe multiple modules, and it continues to lower that size of that gate and to a point where it just doesn't work anymore. So I was curious about that, and I wanted to find out what could be done about that. But also, while I was looking at this, I was wondering, why did they use that cable to go between the 960 and the 963? I had problems with that cable because I had been moving my 960, 963 around in my system to get the best location. And so you move stuff around. And that cable just got to where it wasn't working anymore. The clip on the IC on the 960 got deformed and I couldn't get it to stay on. Well, I was looking at it and I realized, there's an unused conductor in that good Hardy cable that goes between the 960 and the 963. That's a 10 conductor cable, but there's only 8 triggers or 8 gates and 1 ground. So you got 8 gates and 1 ground, and there's a 9th conductor that's not being used. This is a picture of the Q960 circuit board from underneath. You'll see a blue jumper wire that I added to the board. On the right end of that jumper, it's soldered to pin 8 of U15. And on the left side, it's soldered to the trigger out connector. So this picture is showing the trigger out connector from the top view of the board. These traces are red in this diagram, but they're actually green on the board, of course. Pin 9 is indicated right there with an arrow. And then the X is going to be the trace that you have to cut. And that's all you have to do to this board. So back to that drawing, these 2 diodes that are circled were actually in that cable, that skinny cable that went on the back that we're getting rid of. So now we're going to have to put those diodes on the 963. I just soldered them to each A and B bus and faced the cathodes toward each other. And so the last step is to add a new wire between pin 9 and the 2 cathodes that are soldered to each other on the 2 diodes. So let's tackle the signal level issue. So this is a simple buffer for the outputs of A and B. These are 74 HCT14 inverters. We put 2 of them together to uninvert the inverted signal. We have the output of the diode matrix, which has the slightly smaller signal coming into A and B buffers on the left side. As soon as we go through the first stage, we recover our 0 to 5 volts, but it's upside down. We go through a second inverter, flip it back over, go through the typical 1K output, which is all the DotCom stuff uses this technique, the inverter buffer output through a 1K. And by the way, the 2 that we don't use, it's recommended to ground the inputs. And then these go to the 2 output jacks, A and B. Match them up with what's going into it. And you're going to have to add power. So we're going to add a MTA connector, DotCom connector, and as usual, we're going to go through a 10 ohm resistor Two capacitors, a 10 microfarad and a 0.1 microfarad. And then that's going to be our 5-volt supply. That's going to go to pin 14 of the chip. Pin 9 is ground. And that pretty much is it. I do have to mention one thing. The outputs that are going to the jacks, those jacks physically have a 10K resistor soldered across them. But that was for the diode matrix. That's not necessary now with the buffers. However, they're still necessary for the diode matrix. So that means you're going to have to come over here to the A and B input of these buffers and have those 10Ks go to ground. And go ahead and do that. So this is my finished unit using a perf board. You can see the MTA connector up there by the orange wire. You can also see that I removed the 10K resistors from being across the pot and pushed them up and connected them to the actual diode matrix. So you got the diode matrix buses going to ground, and it works great. Now I only have one connector coming over here and one MTA connector for power. Restores my output from 0 to 5 volt gate like it should be, and it works great. So anyway, sharing it with you guys in case you're interested. I know it's kind of technical, but some people are into it. That's it.